Hi class, in this recording we're going to talk about ventilation, moving air in and out of our lungs, our respiratory tract. So as we look at pulmonary ventilation, this is a technical way of just saying breathing. In a word, it's breathing. That's what we're going to talk about. As we breathe in, inhaling, that is known as inspiration, and exhaling is known as expiring or expiration. And this process of breathing in and breathing out is known as the respiratory cycle. One inhalation followed by one expiration. And when there's two kinds of respiration, we can have quiet or forced. Quiet respiration is the lazy, what I like to call lazy breathing. So it's what happens when we're at rest. If we really don't have to think about it that much, and it just happens automatically without us thinking about it. And then we have that forced respiration. This is the breathing in and out with effort. So it's very deep, very rapid. It's typically done when we're exercising or if for some reason we decide to intentionally hyperventilate. And as we're breathing in and breathing out, we have to move a fluid. And the fluid we're moving is air. Air is a fluid. And pressure gradients are going to cause air to move into our lungs or out of our lungs, depending on the gradients. And I've said this before. I'll say it again. Okay, sorry, I lost my train of thought. My kids decided to hunt monsters right behind me. So those were the weird noises you just heard. Back to the recording. So as we're looking at, where was I? Pressure gradients, fluid flow. Oh, yeah. So all fluids flow from areas of high pressure to areas of low pressure. And this is true of moving blood in our circulatory system. And this is also going to be true of moving air within our respiratory systems. So as we use our respiratory muscles, we are going to change the volumes to create pressure gradients that are going to move air in and out of our lungs. So let's first talk about respiratory muscles, muscles that we use for breathing in. The diaphragm is the single most important respiratory muscle. And here's our diaphragm. It folds up into our thoracic cavity. And let's look at the direction of these muscle fibers. Notice that these muscle fibers are going across the thoracic cavity. When we contract the muscle fibers of the diaphragm, they become shorter and the diaphragm is depressed downwards by contracting. And this is going to enlarge the overall thoracic cavity. And when volume goes up, pressure goes down. Volume is inversely correlated to pressure. So here's to put it in math form. If we increase the volume, the pressure decreases. There's that inverse correlation. For those of you who remember your gas laws from your chemistry prerequisites, this is a gas law that you had to cover in your chemistry classes. So as we have this diaphragm depressing, we increase the volume of our lungs, and this is going to account for most of the inhalation, most of the air that we move into our lungs. Another key muscle is the external, went a little farther. Here we go. Is it the external intercostals? And these external intercostals we use for breathing in. When the external intercostals contract, they are going to stiffen the thoracic cage and keep it from caving inwards when the diaphragm descends. And this is going to cause the overall enlargement of the thoracic cage. In addition to stiffening the thoracic cage, they also help to elevate the ribs and move them anteriorly as well. And this is going to also account for approximately 1/3 of the other movement of air into our lungs. There are some other muscles as well that we use to inhale. They include the sternocleidomastoid and the scalenes to help elevate the sternum and the first two ribs respectively. But in terms of the two most important muscles, we have the diaphragm and the external intercostal muscles as the two most important muscles for inhalation or respiring in. And during normal, quiet expiration, here we go. I keep forgetting to click on this pen icon on my screen. During expiration, we breathe out. And during normal, quiet expiration, this is an low energy process. We don't have to input a lot of energy. We instead have a lot of elastic tissue in our lungs, and that elastic tissue causes our lungs to spring back into a a resting state. You could think of our lungs as kind of like a big balloon, and you inflate the balloon, and the moment you let go of the nipple of the balloon, that latex balloon will and air will come rushing out of it. Our lungs are the same way. The moment we stop holding air in our lungs, we will naturally have the air rush out of our lungs, kind of like that latex balloon. And that is normal quiet expiration. So just relaxing the muscles of our thoracic cavity are going to cause, relaxing those muscles causes the lungs to recoil back to their original shape, resulting in a smaller size of the thoracic cavity. And then let's jot down that pressure volume relationship again. So if the volume becomes smaller, so if volume gets smaller, pressure becomes greater, and then we have elevated pressure in our thoracic cavity, causing air to flow out of the lungs. Now, that was normal, quiet expiration. We also can force air out of our lungs. Sometimes the elastic recoil of our lungs isn't enough to force the air out quickly enough. We need to help with some muscles. And to do that, the two biggest muscle groups that we use are the rectus abdominis and the internal intercostal muscles. Other muscles include the muscles of the abdominal pelvic wall, but the rectus abdominis and internal intercostals are the two biggies. So as we look at these muscles, they are going to force the ribs down and force the abdominal pelvic cavity up. And this is going to allow us to force air out. For those of you who've been in choir, this is breathing with your belly, or abdominal breathing. You're supposed to breathe in and expand your belly. For those of you in choir, this is good singing etiquette. When you breathe in, you want to stick your belly out when you're breathing to maximize the volume of your thoracic cavity. And when you exhale, you want to squeeze your abs. You want to contract these muscles of the abdominal pelvic wall for abdominal breathing to force as much air out of the lungs as possible. Now, in terms of controlling breathing in and breathing out, we have respiratory centers in our brain. I'm trying to find a good spot to put this awkward icon. Let's go. I'll tuck it in over here at the corner of our screen. Tuck it there. So as we look at the respiratory centers in our brain, we have a primary generator within our ventral respiratory group. Our ventral, and this is review from Bio 214, but there's a lot of stuff in the nervous system, so it's nice to review this every now and again. So as we look at this ventral respiratory group, the ventral respiratory group is located right here within the medulla oblongata. And we're also going to have the dorsal respiratory group within the medulla oblongata, and then we have the pontine respiratory group within the pons, hence the name pontine respiratory group. So the ventral respiratory group is going to, by default, make us breathe in and out by about 12 times a minute. That dorsal respiratory group is going to moderate or change the frequency of breathing in and out and how deeply we breathe in and out. And this is where we can receive influences, some peripheral nervous system input, some external sources to help us control the rate that we breathe in and breathe out. So information from the peripheral nervous system is going to enter into the dorsal respiratory group, and from there we'll go to the ventral respiratory group. We're also going to receive information to that pontine respiratory group so that it can modify the output that is sent to the ventral respiratory group and dorsal respiratory group. So when we think of the ventral respiratory group, this is the primary rhythm generator. So this is where it all begins. And then based on signals being sent to the dorsal respiratory group from external sources, we can modify that ventral respiratory group, and then we do lots of modifications with the pontine respiratory group that allows us to adapt to very special circumstances, like when we're sleeping and we need to breathe deeply and slowly, or we're exercising and need to breathe deeply and quickly, or when we're vocalizing, when we need to breathe, excuse me, I would refer to that as a non-vocal vocalization. When you burp, when we vocalize, or when we're talking and we need to breathe, have extended exhalations and quick inhalations when we're talking a lot. There it is. Every once in a while, though, we have some problems with our respiratory centers, and we begin to hyperventilate. This hyperventilation process is when we breathe in and out really fast. We have lots and lots of rapid inhalations and exhalations. Usually, hyperventilation is going to be triggered by anxiety, so some kind of a emotional stressor. Or psychosomatic cause will make us breathe in and out very quickly. And the key definition here between for hyperventilation is that we breathe in and out so rapidly that we get rid of CO2 from our body faster than we make CO2. And if we get rid of the CO2, carbon dioxide, faster than we generate it, then we lose carbon dioxide homeostasis. Blood carbon dioxide levels drop. That as we have a drop in the blood carbon dioxide levels, the pH levels are going to increase. pH becomes more basic. That's going to lead to the cerebral arteries constricting. And as we have a constriction of the cerebral arteries, we have less blood delivering nutrients to the cerebral spinal fluid. So we have less nutrient exchange in the brain. And that will cause dizziness or fainting. How do we control this? How do we handle hyperventilation? Well, first, we need to take care of the carbon dioxide problem. This is why we tell people to breathe in and out of that paper bag. So if you're just so excited, you're just so worried, you're so full of anxiety that you're hyperventilating, you need to do that into a paper bag. And by doing that into the paper bag, you can inhale the carbon dioxide that you're exhaling. And that will help you maintain blood carbon dioxide homeostasis. And then and that's just the physiological aspect of it. There's also a psychological aspect of it. When you tell somebody to focus on breathing in and out slowly with the paper bag, to make the paper bag big, make the paper bag small, make it big, make it small. A lot of times it calms the person down. Focusing on blowing up and making a bag big and small helps them not to focus on whatever it was that triggered the anxiety in the first place. So it's, the paper bag, it's a 1-2 punch. It has a physiological and a psychological cure for hyperventilation. Now, in terms of voluntary control of breathing, we talked about those respiratory centers within the pons and medulla oblongata already. We also are going to have voluntary control up in our motor cortex of our cerebrum. And and this is kind of cool, we can involuntarily and voluntarily constrict the skeletal muscle of our diaphragm. So within our cerebrum, the higher brain, we have our motor cortex that can send impulses down to the respiratory neurons in the spinal cord. We can completely skip those respiratory centers and go, give me a second here. We can go all the way down to the lungs directly through the cortical spinal tract, bypassing the bulbal spinal tract within our spinal cord. What does this mean? This means we can choose to breathe in deeply and hold our breath. Or when we smell something that's very stinky that we don't want to smell, we can just stop breathing in for a little bit of time and walk past the stinky smell that smells or the smelly smell that smells. However, there's a limit to this. At a certain point, blood carbon dioxide levels are either so high or so low that the autonomic nervous system takes over for the voluntary nervous system, and we are unable to hold our breath any longer or hyperventilate any longer. If you hyperventilate too long, eventually you'll pass out and your breathing will slow down. If you hold your breath too long, eventually you'll pass out and your breathing will go back to normal. Now, as we look at the ability to move air in and out,